An alert wakes you up. There is a process on your server eating CPU named to look like a normal piece of Linux, but you do not recognize it. So, is this box hacked? Think of it as a break-in. An intruder is inside, wearing a staff uniform so nobody looks twice. Our job, like a calm detective, is to prove who they really are, find every way they left to sneak back in, and change the locks. All in a safe lab on a server we own. Let's go. First instinct test. You spot a suspicious process pretending to be a kernel thread. What do you do first? Be careful here. The wrong move destroys the very evidence you need. Pause, lock one in, and we will prove the right answer together. Here's our suspect. On screen it looks just like a kernel thread. Square brackets, a kernelish name, that is the uniform, it is dressed to look like staff. But notice two things. Its parent is process 1, not the kernel, and a real kernel thread would not show a normal command line like this. Suspicious, but a uniform is not proof, so we investigate calmly and we do not kill it yet. Let's see what is actually listening on the network. SS shows open sockets, -L only the listening ones, secure shell on 22 that is normal. But this, port 4444, opened by our imposter. A real kernel thread never opens a network port, that is a backdoor. Now the move that ends the argument. Every running process keeps a link to the exact file it was launched from under proc, we follow it, and there it is. The program it is running was already deleted from the disk. Deleted but still running. That is a classic hiding trick and no normal service does it. The uniform is off, now we have proof. And if an interviewer asks how you tell a fake from a real kernel thread, this is the line. Check proc, PID, exe. A real kernel thread points to no file at all. Now and only now we kill it. We grabbed the evidence first. The open port, the deleted file, so we know exactly what we are dealing with. The process is gone, but do not relax yet. Killing the process is the easy part. If it left itself a way back in, it will simply return. How does something survive a reboot or come back after you kill it? It hides on disk. First place to check. SUID files in the wrong neighborhood. A SUID file runs with the powers of its owner, and if that owner is root, anyone who runs it becomes root. We search the places these should never live, and one turns up. Look closely. That little s in the permissions is the SUID bit, and the size gives it away. It is a copy of the shell, owned by root, with SUID set. In plain words, a root key for anyone who knows it is here, dressed up with a boring, official-sounding name. Second hiding place, scheduled jobs, cron tab-L lists them, and here is how our process was going to come back. A cron job every 5 minutes relaunching that exact backdoor. Kill the process all you like. This one line brings it right back. So we pull out both roots. Delete the hidden root shell and remove the rogue schedule. Now when it is dead, it stays dead. Let's generalize this, because it is the part that trips people up. Killing the intruder is never the end. A smart one always leaves a way back in. Place 1. Scheduled jobs, cron, and systemd timers. Think of it as a window they left unlocked to climb back through. Place 2. Things that run at boot. A rogue systemd service or a startup script quietly launches it again on every single reboot. And place 3. A SUID root shell tucked away somewhere. Think of it as a spare key hidden under the doormat. So even if you clean everything else, they keep a one-command path straight back to root. Check all 3 every time. One question left, and it is the most important one. How did they get in? The auth log remembers every login attempt. Let's count the failures. 5 failed passwords in a row from a single address. That is a brute force. Somebody sat there and guessed. And then the line you never want to see. Accepted password. The guessing worked. They walked in as a real user using a password, so the way in was not some fancy exploit. It was a weak password and the fact that password logins were allowed at all. We shut that door for good. We turn off password logins entirely. From now on, only a real cryptographic key gets you in. A password can never be guessed again because a password is no longer accepted. Then we forbid logging in directly as root. Admins log in as themselves and then step up. It means one stolen credential is never instantly the entire machine. Never trust an edit you did not reread. We check the config. Both lines now say no, passwords off, direct root off. And restart the service so it takes effect. Done. The box is now key only. The exact door they walked through is closed. The playbook, see a suspicious process. Do not kill it first. Investigate it. Its open ports and the file it was launched from. A deleted executable behind a running process is a giant red flag. Normal software simply does not do that. Then clean every way back. Scheduled jobs, startup units, and hidden SUID shells, or it returns. And close the door they used. Keys only, no password logins, and no direct root. And the honest seniors rule. If you cannot prove the box is fully clean, you do not clean it. You rebuild it from scratch. Here is the write-up. Back to the break-in. One weak password over a login that still accepted passwords was the unlocked front door. The intruder walked in, put on a uniform, the fake kernel thread, and left 2 ways back an unlocked window, the cron job, and a spare key under the mat, the hidden root shell. The lesson that lands in interviews. When you suspect a breach, do not panic and do not kill first. Investigate, then remove every layer of persistence, then close the entry point. And if you cannot prove it is truly clean, you rebuild. That calm, layered approach is exactly what separates a senior from a junior. Case 4 closed. Detected, cleaned, and hardened the calm way. If this made server forensics feel a little less scary, subscribe because the next case is pure dread. A routine, planned reboot, and the server simply never comes back up. See you there.